Okay, so 2.3 is basic limit laws. This section to me, it's relatively self-explanatory, and it reminds me of when we learn all of the associative property, distributive property, commutative property of real numbers. So same idea. We're going to be looking to evaluate limits algebraically, but in order to do that, we have to apply these limits. So our first limit that we're looking at here is that the limit of any constant k as x approaches some number c, it's always going to be k. If we think about that graphically, it's because if we graph a horizontal line, a constant, it's a horizontal line. So some constant k would be here. So any x value that I approach along this line, the output, the y value, will always be k. So that is what you want to think about as you are evaluating limits of constants. Okay. The second one is talking about limit of x. Well, again, think about it graphically. So x is the line that travels through 0, 0, has a slope of 1. Right? So at any given x value, because of the slope being 1, the y value is the exact same thing. So if this x value is a c, then this y value is also a c. So at any given moment, the ordered pair is exactly the same for x and y. And therefore, if you're looking at the limit of just x, it's going to equal whatever the constant is that we are approaching. Here's some more basic limit laws. Okay. So first of all, the limit of f of x and g of x have to exist as x approaches c. And then we can essentially break up this sum or difference, and we could distribute, quote unquote, the limit to each of them and evaluate them separately. So we can expand through addition or subtraction. If we have a coefficient in there, right? That coefficient, because it does not have an x value of itself, can be pulled out in front. And we can apply the limit just to the function. Again, only if this is a constant k, like a true coefficient. If we are multiplying two functions together inside of a limit, we can break that apart also through multiplication. Similarly, with an exponent on a function, we can pull that exponent out so that we're only taking the limit of the x of the function. Okay. And lastly, we can do this for division given that g of x does not equal 0 at c, because that would make this undefined. So as long as g of x or g of c does not equal 0, then we can take the limit of the numerator and the denominator separately. So this next one, the example is just shown for us, right? So using basic limit laws to evaluate. Limit as x approaches 2 of x cubed. We can think about this from the previous lessons, that x cubed, yeah, that's a continuous function. I don't have a domain restriction, so if I'm evaluating this limit graphically, I'm not looking at a hole. I should be looking at a filled-in circle or a filled-in point on the graph. Using basic limit laws is asking you to essentially extract the operations out of the limit so that we can isolate this limit x. Because as soon as we can isolate either a limit x or a limit of a constant of k, then we can evaluate those. Those are the two rules that we are told how to do right now. Okay? So then as soon as we have limit of x as x approaches 2, well, we know that that takes on the answer of 2. Then we apply the operation afterwards and get 2 cubed or 8. So same idea here. I'm going to distribute this limit to each of my terms first. I'm expanding this. And then it's the limit as x approaches 2 of 5x plus the limit as x approaches 2 of 7. I can further expand and continue to remove all operations inside of these limits. And I have the limit of x as x approaches 2, quantity cubed. I have 5 times the limit as x approaches 2 of x, and the limit of 7 as x approaches 2 is already fine. So now I have isolated, right, those limit x's and those limit constants. And now I can evaluate. So limit of x as x approaches 2 is 2 cubed plus 5 times 2 plus 7. 8, 10, 7, 25. All right, so yes, all that we are doing here is expanding, following order of operations, and getting the same exact answer. Okay, so in this section, you're meant to understand that these can be expanded, that you can always break it down to its simplest form and evaluate that limit x, that limit 7. In a problem like this in the long run, will you need these basic limit laws? Absolutely not. But in more complicated ones where we're trying to prove things, every once in a while this will come up. Okay, so I'm not going to expand it fully. Notice the inside is exactly the same as what we just did. All right, we just have this extra square root symbol. So same thing's going to happen. I would follow the same expansion, and then I would have this overarching square root, or 1/2 power. So ultimately my answer would come out as 5. Okay, so I'll take the moment to expand this one. We have a fraction. We want to ensure that if I did evaluate the denominator at -1, I would not get 0, and I'm not going to. So I can proceed and say that this is equal to the limit as t approaches -1 of t plus 6 divided by the limit as t approaches -1 of 2t to the 4th. Okay. The numerator I can expand with addition. The denominator, I have an exponent and I have a coefficient. So 2 parentheses limit as t approaches -1 of t to the 4th power. So the placement of my parentheses was important, right? That 2 is not being raised to the 4th power. So now I have -1 plus 6, 2 times -1 to the 4th. 5/2. Another example for you to try, but I'm going to skip it for now. Okay, hold on. All right, lastly, this is an example where if I simplified first, I could get an answer. But if I follow these limit properties, right, and I write this as a fraction, this is undefined. G of x is not defined at 0. Therefore, I can't follow the same properties. So I don't want to get the fact that I have a 0 over a 0, because that's not allowed. So this is a case where the function's not defined, but I could simplify this and say, well, this is the same as limit of x approaching 0 equals of 1, and therefore it equals 1. So this is something that we're going to investigate more and more this chapter, whether the function's defined, not defined, what type of discontinuity might it have because of this.